In the hush before dawn, three heartbeats thunder in unison. One belongs to a marathoner slicing through Nairobi's thin air, another to a swimmer carving a silent vacuum down an Olympic lane, the third to a weightlifter suspended beneath 200 kilos of iron. The roar of a stadium is hours away, yet inside these bodies molecular storms already rage. Buffers saturate with acid, mitochondria ignite. Welcome to the unseen frontier where champions are built cell by cell. Love what you are watching? Scan the R to join the community. From the outside, elite performance can look like sorcery, a blur of flawless limbs and impossible endurance. But pull the camera inside skin and bone, and sport becomes a story of adaptive biology. Training is essentially controlled trauma. Muscles tear, hormones spike, neurons rewire. Over months and years, the athlete's body rewrites its own blueprints, tilting every variable towards speed, power, or efficiency. This documentary traces that metamorphosis, from red blood cells multiplying at altitude camps to neural circuits that fire hundredths of a second faster after 1,000 repetitions. We'll travel through physiology labs, MRI suites, and wind tunnels, listen to cardiologists decoding ECGs, and sit with sports psychologists who teach breathing patterns that calm a pulse on center court. Yet every breakthrough carries a price tag of pain and precision. First, the pump. An untrained heart beats roughly 70 times each minute. In an elite endurance athlete, that number can drop below 40 because each contraction ejects almost twice the volume of blood. Echocardiograms show walls thickening, chambers ballooning just enough to meet increased demand without tipping into pathology. Capillarization follows suit. Microscopic vessels sprout through muscle like side streets, shortening the commute for oxygen. At the same time, hemoglobin levels climb as altitude tense and hypoxic intervals fool kidneys into releasing more erythropoietin. More cells means richer crimson in every artery, but also thicker blood. So hematologists measure iron stores obsessively to keep flow swift. During maximal effort, the champion's cardiac output may exceed 40 liters per minute, enough to fill a household bathtub in 60 seconds. On an ECG trace, the sinus rhythm looks almost lazy, but beneath that calm baseline lies a reservoir of explosive capacity. For every heartbeat, there must be an equally disciplined breath. Lung size is partially genetic. Rowers famously carry almost twice the vital capacity of average adults. But training teaches the diaphragm to behave like a high-torque engine. Inspiratory muscle drills with resisted valves strengthen the sheet of tissue that domes beneath the ribs, delaying ventilatory thresholds so carbon dioxide can accumulate without panic. In cold rooms at sports institutes, physiologists fit athletes with snorkel-like mouthpieces and map oxygen uptake second by second. The data reveal an art, conserving breaths down the backstretch, purging spent air in a single explosive exhale off the wall, synchronizing stroke rate with tidal volume. Elite free divers pushed this relationship to the extreme, storing oxygen in myoglobin-rich muscle, while the conscious mind sinks into bradycardic stillness. Across disciplines, mastery of breath becomes mastery of time. The ability to lengthen it, compress it, or surrender it entirely for a final decisive surge. If blood and air are logistics, muscle is the battlefield. Strength athletes thicken their filamentous actin and myosin, adding sarcomeres in parallel so each fiber can tug with more force. Sprinters prize type IX fibers, white, glycolytic rockets that empty their glycogen payload in seconds, while marathoners coax type I fibers to multiply mitochondria until they glow under fluorescence microscopy. Bone, often forgotten, is just as plastic. The tibias of long-distance runners gain density in response to repetitive impacts, whereas gymnasts grow cortical bone thickness from tumbling's compressive shocks. Tendons stiffen to store elastic energy and return it like a spring, but too much stiffness invites rupture, so load is periodized carefully. Modern labs fire ultrasound waves through Achilles tendons mid-jump, calculating shear modulus in real time and feeding the numbers back to coaches who adjust plyometric volumes on the fly. The result is a body that has solved the eternal trade-off between resilience and responsiveness. Yet muscle strength means little without neural orchestration. Inside the motor cortex, synapses refine themselves through endless drills, pruning slower pathways and amplifying fast ones. Electromyography shows that expert lifters recruit high-threshold motor units milliseconds sooner than novices, a neurological head start that multiplies gross power. In sports demanding precision, archery, diving, fencing, the nervous system reduces variability, a phenomenon called signal-dependent noise. It does so by batching movements into chunks called motor synergies, saving cortical bandwidth for strategy. At the spinal level, stretch reflexes are recalibrated. Fast swing face hamstrings in sprinters fire sooner, preventing tears that would sideline an Olympic cycle. Neurotransmitters shift too. With habitual intense training, dopamine transporter density drops in certain pathways, allowing motivation to remain high despite fatigue. When you witness a gymnast land blind off the high bar, you are watching a symphony of myelin and electricity play to perfection. Hovering above these tissues is a hormonal command network tuning everything from mood to metabolism. Acute bouts of exercise spike catecholamines, priming muscles for action, while chronic training reshapes the baseline. Resting cortisol often falls and testosterone rhythms sharpen. Female athletes contend with nuances of the menstrual cycle. In the late follicular phase, elevated estrogen can increase ligament laxity, subtly raising injury risk. Smart programs use this data, modulating jump volumes or heavy lifts around hormonal peaks. Growth hormone and insulin-like growth factor 1 surge during sleep, orchestrating repair. Hence the insistence on 9-hour nights in dark, phone-free rooms. Even gut hormones play a role. Peptides released when nutrients hit intestinal walls influence satiety signals that determine whether the athlete meets her macro targets. In essence, the endocrine system functions like an investment bank, reallocating resources toward whichever tissue promises the greatest competitive return. Because adaptation is the alchemy of stress plus rest, recovery practices have migrated from luxury to central pillar. Contrast baths manipulate vascular caliber, sweeping metabolites out of muscle bellies. Whole body cryotherapy, once fringe, now sits beside hydrostatic compression boots in major league training rooms. Athletes wear ECG patches to track heart rate variability, a window into autonomic balance that predicts when pushing hard will sharpen the blade and when it will snap it. Sleep scientists outfit bedrooms with infrared cameras to ensure REM cycles are undisturbed by ambient light or rogue caffeine. Some teams fly charter aircraft retrofitted with circadian-tuned LEDs to minimize jet lag as they chase points across continents. The mantra is simple. You do not grow while lifting a barbell. You grow while lying motionless afterward, the nervous system digesting stimulus like a library digitizing new books for future reference. Fuel is narrative too. Carbohydrate periodization teaches muscles to burn fat at submaximal speeds, sparing glycogen for late surges. Protein timing capitalizes on the so-called anabolic window, though modern studies show the window may be more of a barn door spanning several hours. Micronutrients are calibrated with near-pharmaceutical precision. Even slight magnesium deficiency can derail nerve conduction times. Elite cyclists sometimes ingest ketone esters to shift substrate use, a trend dividing sports dietitians over long-term safety versus short-term gains. Hydration, once a plastic bottle and guesswork, now employs sweat patch analytics that quantify sodium loss so replacement drinks match each athlete's personal recipe. Meanwhile, the gut microbiome becomes both lab and battleground. Probiotic strains correlated with reduced infection days are shipped in coolers to training camps because one ill-timed head cold can unravel a season of preparation. Physiology is incomplete without the theater of the mind. Neuroimaging reveals that elite marksmen dampen activity in the default mode network seconds before a shot, muting internal chatter. Performance psychologists teach self-talk scripts that convert adrenaline into narrowed focus rather than trembling haste. Some athletes rehearse entire races in virtual reality, their brains lighting the same motor circuits as the coming contest. Heart rate-controlled breathing at resonance frequency, around 6 breaths per minute, stimulates the vagus nerve, lowering blood pressure and carrying cognition into the fabled flow state. When catastrophizing thoughts do intrude, acceptance commitment techniques reframe them as weather clouds, present but transient, unable to rule the sky. Unlike muscle, confidence has no NRI, yet coaches watch posture and micro-expressions as intently as split times, ready to intervene with mindfulness drills or a strategic rest to restore the athlete's perceived readiness. What looks like fearlessness is, more accurately, a mastery of recognizing fear's physiological signature and choosing to surf it instead of sink beneath it. Motor learning research shows that champions accelerate myelination of relevant neural tracts, literally insulating skill from decay. Deliberate practice sessions are structured like nested loops. Block practice establishes gross patterns, then randomist drills break complacency and forge adaptability. Slow-motion video feedback, once grainy and delayed, now streams in ultra-high speed onto tablets mid-session. Errors are corrected before they fossilize. Even language matters. Instructing a sprinter to push the ground away yields better force time curves than telling her to extend the hip, because imagery recruits right hemisphere networks tied to spatial cognition. Sleep after skill acquisition consolidates synapses. One landmark study found a 20% accuracy jump in free throw shooting after a full night of rest, compared with an identical practice volume on restricted sleep. Thus, the body remembers not only through muscle, but through rewired electricity, every repetition engraving another line in the athlete's evolving instruction manual. The 21st century added a new player, data. GPS chips the size of coins track meters run and G-forces absorbed, while the inertial sensors inside shoes detect pronation angles on each foot strike. Machine learning algorithms integrate this torrent with biometric streams, glucose, lactate, HRV, to predict injury risk days before pain emerges. Coaches joke that the biggest change to training is charging batteries, yet the numbers reshape tradition. Rugby teams shorten contact drills by 8% once algorithms show fatigue to collision ratios climb past a critical threshold. In Silicon Valley basements, engineers iterate smart fabrics whose fibers double as electrodes, turning jerseys into moving ECG maps. The ethical debate lags behind the hardware. Athletes already wonder where performance insight ends and invasive surveillance begins, a question bound to shape the next generation's relationship with their own bodies. Even sleep is gamified, with rings and scores nudging ultra-competitive minds toward the very rest they once scorned. No exploration of elite physiology can ignore genetics. The ACTN3 sprint allele, the EPO regulating EPOR mutation in Nordic skiers, the myostatin deficiency that endows extraordinary muscle mass. These variants sprinkle through Olympic rosters at frequencies that make statisticians' eyebrows rise. Genotyping kits now sit beside foam rollers in some training centers, guiding talent identification as much as technique drills. But CRISPR whispers at the door. The same scissors that edit diseased genes in embryos could one day amplify fast-twitch fiber expression or tweak pain thresholds. Juarez laboratories already run polymerase chain reactions looking for unnatural sequence signatures in athlete blood. In bioethics panels, philosophers ask if banning enhancement might inadvertently privilege the lucky gene lottery, while coaches quietly wonder how to compete if rivals cross that invisible line. As the line blurs between training adaptation and pre-engineered potential, society must decide whether the concept of a level playing field is technological nostalgia. The physiology of championship also wears gendered faces. For decades, sports science generalized male data to everyone, but recent studies revealed distinct injury mechanics. Female ACLs tear at rates 2 to 8 times higher in pivot sports, in part due to hormone-mediated ligament properties and differential neuromuscular activation. Iron metabolism diverges as well. Menstruating endurance athletes hover perilously close to functional anemia without vigilant supplementation. Energy availability becomes critical. The female athlete triad, low caloric intake, amenorrhea, osteoporosis, has evolved into the broader term RED-S, recognizing that men can suffer similar deficits. Concussion symptoms last longer on average in women's soccer, sparking rule changes in youth leagues. biomechanists now design strength programs that narrow hip-knee valgus angles through targeted gluteal activation, turning statistical vulnerability into biomechanical advantage. These insights do more than protect health. They unlock performance once obscured by one-size-fits-all models, ensuring breakthroughs are limited only by imagination, not oversight. Champions also emerge where conventional physiology charts end. The Paralympic Village. Researchers speak of unique physiology, where amputee sprinters train residual limb musculature to interface seamlessly with carbon fiber blades that return more elastic energy than biological tendons ever could. Wheelchair racers develop enormous trunk and shoulder capacity, their stroke rates rivaling the cadence of able-bodied cyclists. Visually impaired runners sync stride with guides, relying on vestibular and proprioceptive cues heightened by necessity. Neuroplasticity studies show expanded somatosensory cortices in these athletes. Spinal cord-injured swimmers, for instance, recruit core musculature above the lesion level to compensate for leg paralysis, generating efficient vortex patterns verified in Flume laboratories. Functional electrical stimulation bikes now allow mixed neuromechanical pedaling, hinting at hybrid events where biology merges with circuitry. Such adaptations illuminate universal truths about human potential. Limitations trigger creative pathways, and performance boundaries shift when technology, coaching, and willpower interlock. Every physiological edge invites an ethical echo. Altitude houses simulate 3000 meters in suburban basements, legal yet inaccessible to many nations. Blood transfusions cross the line into doping, but altitude tents that provoke the same erythropoietic response remain permitted. Caffeine once sat on WYDA's banned list was removed and could return if consumption trends escalate. Meanwhile, trans athlete participation forces policymakers to reconcile endocrine data with social justice, a debate as charged as any final sprint. The public adores record-breaking moments, yet recoils when the methods feel too clinical, too removed from romantic notions of natural talent. In roundtable discussions, philosophers cite the cascade effect. Once one team adopts a new tech, others must follow or concede defeat, eroding the possibility of voluntary restraint. Governing bodies scramble to define where innovation becomes unfair advantage. At its core, sport is a mirror reflecting what societies value, tolerate, or fear about scientific progress. Peering ahead, researchers imagine exosuits that offload injury-prone joints during training but detach for competition, or personalized nanosensors flowing through bloodstreams, broadcasting cellular stress before macro-scale fatigue appears. AI coaches built on reinforcement learning models could soon design microcycles tailored to each athlete's overnight transcriptome shifts. Gene therapies aimed at osteoarthritis might extend careers formerly felt by cartilage wear, raising questions about the definition of retirement age. And quantum-level magnetoencephalography promises to map intent before movement, potentially letting athletes correct an error while it is still a whisper in the motor cortex. These possibilities glimmer on funding proposals today, but prototypes already blink in university labs, waiting for the brave, or the desperate, to test them. The march feels inexorable, yet history warns that progress seldom arrives evenly. Breakthroughs tend to cluster around resource-rich centers, threatening to widen the gap between global north and south in medal tables, unless policy foots the bridge. So when the lights flare on the next world stage, and a runner seems to cheat gravity, remember the billions of biochemical bets placed in advance. But consider this too. Somewhere in a quiet lab tonight, an enzyme is being coaxed to fold a new way, a circuit soldered to read one more signal, a neuron taught to fire 1 microsecond earlier. Which of these unseen tweets will redraw the boundary next, and at what cost, remains a question no stopwatch can answer. Yet scan the QR for more.